Okay, this is a little demo for how to use the XCTU tool when you have configured a network and you want to know the responses for a given request. This demo shows a network consisting of a coordinator, two routers and an end device. And the tutorial here is about sending an AT command in an API frame for node discovery. And the frame contents transmitted is this one, that are going to be defined in the C program in an array, for instance. And as you can see here, we get actually 3 responses due to these 3 nodes. And another thing you need to recognize here is actually the length you should expect to receive is 25, 25, and 26. Plus 4, as you have a start delimiter and you have 2 length bytes plus the checksum, and therefore 4 extra has to be added. So 29 plus 29 plus 30 is what you should expect to receive. And as you can see it here, it is 3 different responses. So in the C program, we want to use an asynchronously set up to be sure to receive these 3 responses due to delay between them. It's necessary and robust to use asynchron receive mode in the program. So, and if you want to see the responses for each of these, then you have it here, and you need to go to the manual and find the ND node discovery AT command description to figure out what these fields means. And I can say it means actually you get a response from each node with the MAC address plus the network address plus an ID for the manufacturer plus more, which you can see in the manual. And we can scroll down here, then you can see the different parts of the response, and it is a response to an AT command. Therefore, the type is 88, and also that is described in the user guide for the XBee, either Series 2B or 2S. Same for both. And then you have the command, the node discovery command, also in the response. And the status is actually an important byte to look at, because you can eventually get error codes here, also described in the user guide. And the real response is here. And if we look on it, this is the network address and the MAC. So that is one of them, and the second one, and the third one. Okay, let's go to the programming part. And I have written a little demo program which I will upload to CampusNet, so you can use that as an experiment for yourself. And it is here, and it is, as I said, it is an asynchron initialization. I have made a switch case here to control efficiently where I want to be for what requirements, what needs. So it's, if we go up here on the top, we have some definitions, the baud rate and the device, which is the serial device on the Raspberry Pi. And then I have 2 flags here defined. Then I use a little switch case to control the operation of the program. I have an init and send and read in and a result. And then I have a very important function here as we enable asynchronously receive. That means the signal handler will catch when there are bytes in the receiver buffer to be read. So it's pretty much like a service routine, this handler, if you know what that is. And then we have a little transmit function where you transmit what you want to tell your nodes from the coordinator side, as the coordinator is mounted on the Raspberry Pi, so you communicate always through the coordinator to your nodes. Then there is some settings here about the UART, and the Termios has an struct definition, and for the definition of the signal action for the asynchronous operation, we need another struct, and then the receive buffer can maximum handle 255 bytes. And then I go into my little switch case where I have an init, where I open the connection, I get a response, hopefully correct, else I stay here until I get one. Then the settings for the asynchronous handler, the signal handler, is done as this piece of code. And if you like to know more about these flags, then you need to go deep down in the Termios description and follow some of the links I have listed in the slides for serial communication. And here is another thing you need to handle these asynchronously responses. And the flags here, we refer to the baud rate defined up in the top, and 8 bytes, and read, and then we have an ignore parity, and these two flags has to be 0, as we don't have any control characters. Then we operate the asynchronously receive on non-canonically form. For that reason, we have an V minimum, and at least 1 byte should be there to get an response from the handler. And the other things here is to flush the input-output buffer and to set some attributes for the UART thing. And then I jump to state send, and for control I have this hello world. You can drop it out if you like. Next step is to send the command I want to send to my nodes. Here in this case it is node discovery. This is exactly what you saw in the XCTU tool. I transmit it, and then I go to read, and I stay here until I have got all the responses from the signal handler. And to activate it, then this function is necessary to unlock it. We don't use it for anything, just to activate it. And then I have a wait flag, which is controlled from the response handler function, or callback function is the correct name for it. So it's a callback function which catches the buffer when it is filled with some bytes. And then we read the bytes, test if it is having some contents, and it has some contents mainly, and if not, then of course this is not true, and then this if is not true. And then as we get chunks of bytes, it's important to buffer everything up, else we only receive the last one. For that reason I have defined a multiply integer which counts the amount of responses from the signal handler. So I adjust my start index to next position. As you can see here, I read in the previous I into the multiplier, and then next time the handler responds and set the wait flag false, then I'm ready to fill more bytes from my receive buffer into my response buffer. And that goes on until I have got all what I expect to get. And here is an important thing. You need to know the response. It is not just a random number. you should look for it. And this is as in the blocking call example you can find at the CampusNet. We need to know exactly how many bytes we should expect to receive, else it will not work. If we have got all the bytes, then we are able to print them out on the console and compare with the received bytes in the XCTU tool. And then we know everything is correct in our program. This program is not absolutely bulletproof because there is not any timeout. If something happens, we don't get the 88, then the program will be hanging. But it is a nice example on how the asynchronous operation actually takes place. And when we have got all the bytes we expect, then we jump here and print them out, and then we say stop true, and that means our whiles become false and the program stops. So if we go here, then take a little look on it, then we will try here to execute it. So I call this program now, and then you look carefully in the console here and see that we get chunks of bytes, I hope. See, 1 chunk, 2 chunks, and 3 chunks. And if you look here, I have printed out the number received, and this is the last one. It is the 30 number of bytes, and this is 29, and the previous 29. And if we print all out, then we can see 7E is the start limiter, and then we go forward here. That was the first response, and if you count these number of bytes, you will find these 25 plus 4, and then the next start identifier here is, the start byte is 7E, and we go forward here, and then we can go to the last one, it is here, and then you can see 1A, that is 30, and then the rest of the response is found here. And then I have put an udskriv at the last one to confirm we have got printed out, and then I flush the buffers. That's it.